Hello again. This is the last part of lecture 1.5 where we discuss the concept of implicit differentiation. We are going to use the concept of chain rule in parts 1 and 2 to derive the formula for implicit differentiation. We are already familiar with this concept. We've discussed this already in Math 21 or your previous math calculus courses. Let's review how it works by looking at this example. So we have the equation equal to x cubed plus y cubed is equal to 6xy, where y is a differentiable function for x. So this is what we call the implicit definition of the function, where we just write it as an equation involving x and y. So we get the derivative of y with respect to x using implicit differentiation. So what's going to happen is we get the derivative of both sides of the equation with respect to x. So we have the derivative of this expression with respect to x is 3x squared plus this is a function involving x, so we apply chain rule here. So the derivative with respect to y is 3y squared, and then multiply that with the derivative of y with respect to x. Now for the other side of the equation, here we're going to use product rule. So we have 6x multiplied with the derivative of y with respect to x plus y times the derivative of 6x, so that's 6y. So what happens next now is we isolate dy over dx here, and that will give us 6y minus 3x squared all over 3y squared minus 6x. So our objective now is to simplify the computation for the implicit differentiation. So this is the general case. We have y is a differentiable function of x, and we cannot write y in terms of x, but instead we'll use some function of x and y is equal to some constant k. So this gives the implicit relationship between y and x. So we apply the general chain rule from the previous videos. So we have here f of xy. It depends on two variables, x and y. Now, x doesn't depend on anything else, so we have the branch pointing to x here, but this time y depends on x. So if we now formulate the derivative using the chain rule from the previous videos, so when we differentiate with respect to x, so we start from here and end in x. So we have the partial of f with respect to x times the derivative of x with respect to x plus the partial of f with respect to y times the derivative of y with respect to x. But now, since the other side of the equation here is a constant, the derivative of that with respect to x will just give us 0, right? So now what do? Here, the derivative of x with respect to x, we know that to be equal to 1. So we just solve for the derivative of y with respect to x. So that gives us, so we transpose it here, negative partial of f with respect to x divided by the partial of f with respect to y. Yeah, it's actually so easy. We just have to apply this now that we know the concept of partial derivatives. Right? Let me give you some time to digest the equation now for implicit differentiation. If you need more time, pause this video now. Right, let's go back to the example that we had earlier, but this time we'll use a formula to compute for the derivative of y with respect to x. But remember that we must first write this in this format where the other side is a constant. So what do? We transpose 6xy to the other side. So that gives us x cubed plus y cubed minus 6xy. So that's our capital F of xy. And we know that to be equal to 0. So we just use this formula here. The derivative of y with respect to x is equal to the negative partial of f with respect to x divided by the partial of f with respect to y. So looking at this expression, partial of f with respect to x is 3x squared minus 6y. Yeah? Don't forget the negative in front of the fraction. And then what about the partial of f with respect to y? Again, looking at this expression here, that will give us 3y squared minus 6x. Yeah, so that's the answer that we obtained earlier, right? Now, let's try to generalize the case. So this time we have 3 variables. Fun. So let's first solve this the way we solve it in Math 21, shall we? So we have the equation x cubed plus y cubed plus z cubed is equal to 1 minus 6xyz. Here we have z is a differentiable function of x and y. So we will obtain this using implicit differentiation. So again, the idea is get the partial derivative of both sides with respect to x. So that will give us, so what's the partial of this expression with respect to x? That will be 3x squared if we look at this expression here, plus, now why is it 0? X doesn't depend on y. So the derivative of y with respect to x will be 0, right? Now, what about this third expression? Here we apply in chain rule because z depends on x as well. So we first get the derivative with respect to z, that's 3z squared, and then multiply that with the partial of z with respect to x. And now, what about this side of the equation? So this is a constant. The derivative of that is 0. So we're just actually looking at this expression here. So we have 0 minus, but here we have the product of 3 expressions. All right, so again, we use a product rule here. But we can actually combine, yeah. We combine, so this is the left part, and this is the right part. So what's the partial with respect to x? That's 6. Then multiplied with the function on the right, that's yz, plus, all right, so 6x left times the derivative of this expression with respect to x. Y is just a constant. It is not dependent on x. It's only the z that depends on x. So that's why we can just write here y times the partial of z with respect to x. Right, simplifying this expression, we have to distribute the negative sign here. So yeah, we skip some steps here. You can do that by yourself, I suppose. So distribute this, and then we isolate the terms containing the partial of z with respect to x. So that's why we retain the 3z squared here. This is minus. When we transpose it to the other side, that becomes plus 6xy. And then this remains. We have a negative sign here. So that's why you have here minus 6yz. But this expression transfers to the other side. That's why this is negative 3x squared. And then, again, we divide both sides by this expression to get a final expression for partial of z with respect to x, now equal to this. So what happened here is you just distributed, factored out the negative sign here. So that's a negative of 3x squared plus 6yz. That's why this became plus. Right. So now we again generalize the formula for implicit differentiation, just like in the previous case. So, right, I forgot. Here, we compute also for the partial of z with respect to y. You use a similar approach and we'll get this. So now, we try to find a formula for implicit differentiation similar to the previous example. All right. So again, we look at f of x, y, z is equal to some constant. So we don't isolate z in terms of x and y. We just leave it like this. And again, take note that the other side must be a constant. All right. So this defines the implicit relationship between x, y, and z. Right. So these are tree of dependency. So we have f of x, y, z on top. So it depends on 3 variables, x, y, and z. X just depends on x. It doesn't depend on y. So that's why there's only one branch here. Y just depends on itself. It doesn't depend on x. So that's why there's one branch here. However, z is dependent on the other 2 variables, x and y. That's why there are 2 branches over here. Right. So we use chain rule again to formulate the partial of f with respect to x. So we are going to look at this path here and this path here. So when we differentiate with respect to x, we get this, the partial of f with respect to x times the derivative of x with respect to x. This path doesn't have x on it, so we just look at the last one, partial of f with respect to z multiplied with the partial of z with respect to x. Right. Again, this is just equal to 1. So when we isolate, and again, since this is a constant, the derivative of that with respect to x is 0. So our objective now is to solve for this expression, the partial of z with respect to x. So this is 1. You just transpose this, divide it by this, and we get this expression here. The partial of z with respect to x is equal to the negative of the partial of capital F with respect to x divided by the partial of capital F with respect to z. So using a similar approach, we can solve for the partial of z with respect to y. So we'll do this all over again, but this time you considering the paths that end in y, and we'll end up with this expression. The partial of z with respect to y is equal to the negative partial of capital F with respect to y divided by the negative partial of capital F with respect to z. All right? So again, we go back to the example that we had before, but we use the formula to find the partial with respect to x and the partial with respect to y. So again, we have to write it like this, where one side is a constant. We can just leave the 1 here and then just transpose negative 6xyz to the other side. So we let capital F, so once we transpose this, that gives us x cubed plus y cubed plus z cubed plus 6xyz. Now take note that this is equal to 1. K is equal to 1 here. So using the formula, the partial of z with respect to x is equal to the negative of the partial of capital F with respect to x divided by the partial of capital F with respect to z. So that's now equal to, so we have the negative here. Looking at this expression, the partial of f with respect to x is 3x squared, not here, not here, here, plus 6yz, right? Divided by, again, going back to this expression, was a partial with respect to z. This doesn't depend on z. This one doesn't depend on z. This one does. So we have 3z squared plus, also this depends on z. So we have plus 6xy. Right, so that's the answer that we have earlier. And again now, for the partial of z with respect to y, again using the formula for implicit differentiation, that will be the negative partial of f with respect to y divided by the partial of f with respect to z. So again, that's equal to negative. This expression, what's the derivative with respect to y? We don't look at this. This one is, the derivative is 3y squared plus the derivative with respect to y is 6xz over, again, we just copy the partial of f with respect to z here. So that's why we get 3z squared plus 6xy. All right. So you can go back to the other solution that we presented earlier, and you will see that we got the same answers as before. But this is a lot easier because now you have a formula for the partial derivative. All right. Okay, so let me just leave you with some exercises to try on the concept of chain rule and implicit differentiation. All right. So just pause this video if you want to try the exercises for yourself. And if you're kind of stuck, you can just consult your teachers in Math 23. All right. Okay. Bye.